In this chapter, we'll talk about the stability and frequency compensation, especially on the two-stage amplifiers. This is a typical negative feedback we had learned before. So we have X and feed for the gain, and the feedback gain beta. For this construction, we know that overall feedback closed loop response is like this, right? Gain. So if you do some perturbation analysis, let's say if the input goes up, the output of the subtractor goes up, the output of HSO goes up, then feedback goes up, and then it goes down, right? Coming back, it will go down. So inside the signal, inside the circuit, it try to make things not change, right? So we want to recover from small external variation, track the input variation, and make it less effective. So this is negative feedback. And then what happened, according to this equation here, if the beta H, the loop gain, if the loop gain becomes -1, right? Loop gain, if the loop gain becomes -1, then what would happen? For that case, we can see that the magnitude is equal to 1, and the angle of the loop gain is the angle of the phase response is -180 degree, like 180 degree, which means thing is -1. Then according to this the equation, it will be, right, goes to infinity, right? The output response will be infinity, right? So why it happened? Because let's say if there's any perturbation at the input, it will go up and up, but because of the phase shift, it will make it go down, like the output change, it will go down, right? And then it will propagate through the feedback and then coming back, then even make it larger variation. So this will grow and go up and up. So it will go to the infinity, right? So the thing that the condition for the loop to be unstable is that the loop gain is greater than or equal. So LG, loop gain, is greater than equal to 1 at 180 degree phase shift point. Right? Then the overall loop feedback becomes positive, right? So loop can be unstable. So in the previous example, I only specified, show that the visualize this loop gain is -1 case, but it can happen even with any even larger gain. Negative gain will result in a positive feedback, right? So this is something that we have to avoid. So we will see how we can avoid this unstable condition. Let's take a look at its behavior in body plot. So if you plot the loop gain beta H, then you will get thermal gain over frequency. But because of each pole there, each pole introduce 9-degree shift, and here and there, so up to here will be two-pole phase, two-pole. Because of two poles, we will make a phase shift of the 180, and then additional shift will keep going down, right? For this kind of loop gain transfer function, so at any point, so at this point here, 180 phase shift point. If you look at the gain here, is greater than 1, right? This is a log scale, so 0 dB is like 1. So if this additional gain is seen here, it will be unstable. So for the stable case, if you see here, for 180 degree phase shift point, if you look at the gain here, gain is less than 1 a beta loop gain. Loop gain is less than 1, then it becomes the stable, right? In a typical amplifier, we design the beta less than equal to 1 because typically we use the circuit for amplification. In some cases, if you want to reduce your signal, then you design the beta greater than 1 so that your output signal is attenuated. Okay, so for usual conventional case, the beta is in the range of the 0 to equal to 1. So in that case, so loop gain, so the loop gain would be what, beta h here. So in this loop gain, if the beta is 1, it will have highest loop gain curve shown in here. If you have a different beta here, the overall curve will shift down without changing, right? Without changing phase response. Same, right? For beta. So for different beta, we have the still same phase response, right? So if you make this let's say this is the 180 degree point. Let's say 180 degree point. If you have a lower beta, it might be, right? It might be in terms of the stability, it get better. It helps, right? If you have a too much gain, then the gain at the 180 degree will be greater than 1. So the loop gain will be too large and the loop will be unstable, right? So you can see the worst case when you check your the circuit or amplifier or whatever. The worst case becomes beta equal to 1 for typical cases, right? So when you analyze your feedback, if inside your feedback, if you have only one pole, so that the loop gain curve is like this, single minus 20 dB per decade, or this is called the single pole roll-off. If you are seeing just single pole roll-off, the maximum phase shift is only 90 degrees. So the feedback is absolutely stable. So this is the unconditionally stable, right? But the situation is different. Once you have a two poles, right? The maximum phase shift is the 180 degree, and the 180 degree, so we will have some ambiguity. So we will have a very close 180 degree phase shift. We will have a very so the loop gain is very close to 1, right? Loop gain becomes very close to 1. It poses it poses this instability issue. So the weak, in that case, we need weak feedback is required. So we have to bring this loop gain, bring this down, right? So that the within omega u, we don't see we just see the single pole roll off. The second pole must be beyond the omega u, right, to make it stable, right? We will see more closely on regarding to that the condition, exactly how far this F2, omega 2, omega P2 should be, how far omega 2, omega P2 should be greater than omega u, right? This is for stable operation. So typically 3 poles and 2 poles system. So within omega u point, if you see the 3 or 2 poles, then you can treat that the system is unstable. This is unstable. Why? So what we'll see. So if we, let's say for example, for 3 pole, definitely at 180 degree shift, we know that the gain would be greater than 1. For the 2 poles at 180 degree shift, phase shift, the gain is near 0, near 1. Loop gain is near 1. So once you close the loop, the closed loop response that at DC gain is 1 over beta, but the near omega u, this is near omega u, the response will have a peaking, so it becomes unstable. Okay. Now, so when you look at the amplifier, you have to identify whether this amplifier has a single pole amplifier or the 2 pole amplifier or 4 pole amplifier. For example, so we have to consider when we count the number of poles, we have to consider the dominant pole position, the number of a dominant pole. For example, this kind of a cascade amplifier, definitely we have an internal cascade node that will cause the, let's say, the additional pole here, and also pole at the output. But if you compare the pole location, the output impedance Rout is very large, right? Compared to the input internal node 1 over GM. This is, let's say, M2, and GM2 is the impedance looking into the source node. So this Rout is well, much greater than 1 over 2M. So we can see that, we can say that this kind of amplifier is used inside the feedback. One dominant pole is here, very low frequency, and the second pole is much higher frequency at the higher frequency. In that case, we can say that this is a single pole amplifier. So, right? So this is one, the frequency, that's omega 1 over Rout times CL, and this second pole location is 1 over that's a GM2 over CX, right? Now this unit gain frequency here is a GM over CL, right? GM1 over CL, this is the M1, and GM1 there, right? So this is called the single pole amplifier. On the other hand, on the right hand side, we have a similar amplifier stages 1, 2, 3, right? R and R. If you design 1, 2, 3, the different resistance there, even though you use the similar resistance, the order of magnitude difference is not that big. So R1 and R2 and R3 are very closely spaced. So this is the C1 and this is C2 and let's say C3. The time constants R1 C1 and R2 C2 and R3 C3s are or similar, meaning your amplifier will have a very 3 poles nearby. So 1, 1, 2, 3, right? So this kind of a closely spaced amplifier will cause a very large phase shift, right? This is something that you don't use typically without. So this kind of amplifier require very large separation of each poles to make it really works. So this kind of amplifier, as you call the multi-pole amplifier, as you can imagine, the number of poles is the 3 poles, right? So this is very important to understand how many poles, dominant poles, are there in your circuit, right? That's something that you have to identify when you consider different amplifier topology inside the feedback. There's just some terminology to define the stability, how stable the loop is. We can identify by looking at the phase margin and gain margin. The phase margin is defined by the when your gain is equal to 1, loop gain equal to 1, look at the phase, the difference between 180 degree to current phase shift, then you get the phase margin. Larger the phase margin, it becomes the stable. For example, if the phase margin is not enough, when you close the loop, you will see like a peaking response. What you want to have is like without peaking. This is nice response was the expected, but with the less phase margin, you get the this kind of a peaking in frequency domain. In time domain, you will get the kind of for the step input, you will see ringing like this, right? This is something that you don't want to have, right? And also the phase margin and for the gain margin you hear. So when gain margin is seen when your phase is 180 minus 180 degree, and then look at the gain amount of the gain, right? Then the difference between the gain and the 0 dB, the difference gap is the gain margin. Right? So the phase and gain margin is large enough, typically large enough, then you will get a nice response for the frequency domain and time domain, right? Typically for the phase margin, we design for the PM, design for the 70 to 60, around that value, and the gain margin around greater than 6 dB. Greater than 6 dB is quite something that you wanna achieve for, right? Let's calculate this special case when your second pole is exactly same as omega u, unit gain frequency. In that case, you will get the phase margin of 45 degree, right? So for that case, in frequency response, if you close the loop, you're peaking. The response peaking is 1.3 times larger than the flat band gain. So this is the amount of peaking you would expect is 1.3 times peaking. So 30% larger peaking is approximately 3 dB larger gain, right? Approximately 3 dB peaking. So definitely, if you wanna have a smaller gain, like smaller peaking, let's say 10% peaking is tolerable, for example, this 10% peaking is required, then you have to design design this phase margin higher, right? So we will see how exactly a peaking response is observed. We will see the detailed number in the following rest of the slides. Okay. For the optimum phase margin, so we design like a 60 to 70 degree for fast settling. If the phase margin is 45, you will see like this kind of ringing for the step input. For the step input is applied, your output is like a ringing. For phase margin 60 degree, you will get the nicely slight overshoot is observed, and it will settle. If you have a even larger phase margin, then what you have is that you will get the nicest settling, but the settling time is slower than phase margin of 60 degree. For 60 degree, you will get the like this. Let's say this is 60. So this slow response is 90. So this kind of for settling behavior must be considered both the slowing and the nonlinear device characteristic. So far we just assume that all the parameter is a small signal all the analysis are based on the small signal analysis, meaning we linearize the characteristic, right, at the operating point. Let's say, for example, for VGS and ID, so VTH here, something like that, right? So we linearize the operating point. The actual response is like something like a non-linear response, right? So operating point here. So the large signal simulation must be run, right, to check the overall this kind of response. Just checking phase margin is not enough, right? Just checking PM is not enough. What you have to rely on is the large signal transient response. The transient simulation is required. And simulation is a real response. Why? Because it covers the large signal behavior. So you must always check the large signal behavior by running transient simulation, right? This is some example. You run this you check the phase margin in this circuit. You check that phase margin is 65 degree, but when you run the transient response, you will get something like a large ringing. This why? Because this kind of amplifier has limited signal range for the input and an output, right? Then also the operating points are all different for all different level of the input and an output, right? Different level, right? This is a larger signal, right? If your circuits are well designed, your operating point should not change that much, but the people ignore this large signal behavior. So most of the case, the people neglect those effects. So you have to make sure that small signal parameter doesn't vary, right? Why doesn't vary? How you can make sure that? So for all the signal range, all the transistor, right, is in the desired operating point. usually the saturation region, right? If you don't have enough margin, then your output, your amplifier characteristic becomes different. So in that case, you may get some different small signal parameters and get some unstable ringing. Okay. And also the student when student design a circuit, they just check the PM, not checking the gain margin. So sometimes the gain margin also critical, because if you, for example, this is loop gain, beta H. So the straight this is omega U and omega P2. The typically this kind of the 20 or 1 pole roll off is expected the response, but sometimes a student may see this kind of zero response, right, and then follow like this, right, or any pole will get there. So if you look at this quite long amount of frequency range, you get the very it doesn't go down, doesn't go follow the 20 dB per decade the slope, single pole roll off, it just becomes flat. So in that case, for example, phase might be phase margin, for example, gain, and you will see the phase here. This ding, this kind of thing can happen by the zero or left half plane zero or right half plane zero, right? The zero response will make things something like this. Wait a second. This kind of phase shift up is caused by what kind of zero you might have. So left half plane, positive zero or negative zero. So negative zero, right? Negative zero might cause like this, and the positive zero make things go in, this is a positive zero. Zero may cause that, right? And then additional pole may, let's say, additional pole will move the phase shift down. So this kind of a shift caused by the negative zero. So in this example, you will see some like by having zero there, you get larger phase margin. This is, let's say, that's a 180 degree, 90. You get the very large phase margin, but you get a lack of the gain margin. The lack of gain margin also make your settling very slow for the time domain input. Very slow transient can very slow settling. Settling is can be observed, right? So we have to avoid this kind of a lack of gain margin by further move down, right? Or like this, right? Move this response to have more gain margin, right? Okay. So gain margin is observed where the phase is 180 degree shift, right? For example, like this, right? Okay. In this chapter, we will learn about the how we do the frequency compensation, so that we can make the loop the stable. So our goal is to make the multiple pole system into a single pole like system. For example, if we have a we know that the single pole response loop gain, for example, A0 is the open loop gain, and then for the feedback factor is equal to 1, right? In that case, the only single pole below omega u make the loop absolutely stable, because we have an only 90 degree phase shift and the phase margin of 90 degree, right? And then if you have a second pole exactly on the GBW here, omega u, or fu, this is f axis, so fu, then what happened? The PM become, right, 45 degree for a GBW equal to F2. So the location of the F2, second pole position, this is F2 is non-dominant pole. So it is important to place this non-dominant pole beyond this omega u, right? Then your phase margin, right? GBW beyond F2 beyond GBW satisfy PM greater than 45 degree, right? So this is something that we wanna have, or to make, we wanna get out of an open loop loop gain response, right? This is the example. What happened if the second pole is within the omega u? If you extend it like this actual omega u happen just below that single pole roll-off position, right? It goes down here. So if the second pole is below the omega u, then your phase margin will be smaller, right? So your loop will be, as you can see here, you are not seeing you're not seeing enough phase margin here. So we check this with the feedback factor equal to 1, which is the worst phase margin scenario for the typical case. So the OPM is verified by this configuration. So if you don't have enough phase margin, you get the peaking with the closed loop response here. So this closed loop response having peaking is irreproducible behavior. So if the behavior is changing, you cannot rely on this kind of peaking response in your system function. And this is the and also additional negative point of this kind of a large peaking is it amplifies noise as well inside the circuit. So your output will be very noisy. So in that way, we want to avoid peaking, right? No peaking is something that you want to have. So this plot shows that when the second pole is exactly at the omega u, then you get the 45 degree phase margin. Even with the 45 degree phase margin, if you close the loop, you will see amount of peaking. How much peaking you are seeing? It will be this 1.3. So without peaking, the flat passband response gain is 1, and this maximum peak is 1.3. So we get the 30% larger gain. And at near bandwidth, right? Cutoff near bandwidth frequency, right? So closed loop bandwidth is defined by this, the omega u of the open loop gain. Omega u of the loop gain actually determine the closed loop bandwidth. This means the near FU of loop gain. Okay. So our goal is how to push this F2 even further higher frequency. You wanna make this FU even higher frequency. Okay. Let's say if we push this F2 higher, so that you may get, let's say for example, a certain larger than 45 degree, right? If you place F2 3 times larger than GBW FU frequency, in that condition, if you calculate the phase margin, for that case it is 70 degree phase margin can be achieved. So this is something that initially when you design the closed loop, you design for this kind of rough idea. We get the design for F2 near 3 times in GBW. That gives us a phase margin of 70 degree, right? So this is something that you design in the initial design, targeting phase margin of 70 degree, okay? There's some derivation. We open loop, two pole open loop gain response. We have a pole at F1 and an F2, and with the unit gain feedback, closed loop gain will be A over 1 plus A. That give us the final second order response here. The eta is the damping factor. That can be also considered as that can be represented by the quality factor Q here, that is 1 over 2Q. The FR is the resonant frequency when the loop is unstable, right? That is near the GBW or FU. So the resonant frequency and FU is kind of relationship. It's resonant frequency is square root of the GBW times the second pole location, and the phase margin can be calculated like this according to the equation that we got. So we calculated several cases. For example, F2 is 3 times larger than GBW, then we get the exact phase margin as a 72 degree phase margin, and the peaking in the frequency domain, there's no peaking in frequency domain, and peaking in time domain is only 4% peaking. So time domain, if you apply the step input, you will get only how much? So 4% increase, 4% peaking is only observed, and the frequency domain you get the, let's say 1 closed response peak. There is no peaking, right? If you if your second pole, non-dominant pole location is close to GBW FU, then you will get larger and larger peaking, right? If the same location, if the F2 and GBW is the same, then we get the 45-degree phase margin. And that leads us what? In time domain, we have the 30% larger peaking, right? 30% larger peaking than the desired value. And also in the frequency domain, we get the 25% larger peaking. This is the this is in dB. I'm sorry. This is the 1.25 greater dB, 1.25 larger 1.25 dB larger peaking, right? Okay. And this is 0.4 dB. This is dB, 0.4 dB. 0.04 dB. This is not the percent here. Very small amount of the peaking here. So for the 1.3, it's 30. Let's say 1.3 is the peaking in dB. I think this is just the linear scale, I guess. That's the point. This is not the dB probably. This is 30% larger. Again, this is this is time domain. I'm sorry, time domain, 30% larger. All right, this is the 4%. Right, this is the dB scale. This is the time peaking in the linear scale. This is the dB scale. Oh no, this is all the linear scale, I guess. So if you have around 45, you get the 25% larger peaking, meaning what? Around 3 dB. Around 3 dB peaking. Around that 30% larger peaking is corresponds to the 3 dB, right? So as you can see in this example, so you can see that definitely you want to design the loop in this the condition at first trial. Okay. This is the actual simulation result. You can see that if the eta, if you remember, so eta equal to, let's say, 0.5 for PM equal to 45 degree. So for that case, around here, around the peaking is a 3 dB peaking, right? 3 dB peaking in the frequency domain, and then the in time domain, how much the 3 dB is around 30%. So here, right, around 0.5, you get the 30% peaking in time domain, right? So as you can see, for the best compromise, is the damping factor eta is between 0.7 and 0.8, which corresponds to phase margin of the 60 to 70, right? So this is something that you want to design for the feedback, okay? And if we haven't looked at for the point eta equal 0.7, that corresponds to PM around 72. That was 72 degree, right? For that 72 degree, let's say 0.7. There's no peaking, right? No peaking in frequency, right? And in in time domain 0.7 around what? Around 3%. Very small, right? Around 3%. The small. What was that? Was that 4%? Was it around 4%? 4% peaking in time. Right? Very small bit. So it's 10% and around 4%, right? Peaking time domain. Okay. So it is, as we have looked at, it is important to identify the location of the second pole in your amplifier. So for example, one stage amplifier, we have a one telescopic amplifier and a folded cascode amplifier. The dominant pole will be definitely at the output because it has large output resistance and the large capacitance at the load. So this will be what? The omega P2, right? P1, this is dominant pole location. The non-dominant pole, omega P2, will be internal load shown in here. For example, this cascading node. So at the top, we will have a 1 over Gm, right? 3. And then capacitor, C total, would be the CS from the M3 and the drain from, right? CD from M1 device, right? So this is something. So two devices contribute to parasitic capacitance, right? For the similar size, we have a 2x larger parasitic capacitance of the single transistor parasitic, right? For the folded cascode, on the other hand, in this case, the impedance looking up is 1 over Gm3, similar, but for the capacitance is larger than the telescopic because we have input parasitic C. So C total is what? So C total here is CD1, right? Let's make it capital. CD1 plus what? CD5 and plus CS3, right? Source node of the parasitic. So we have three parasitic, three devices, parasitic coming in here, and we have the two devices contribute the parasitic capacitance. As you can see, you can imagine that the telescopic second pole location will be higher than, right, folded case, right? Because it has the telescopic has the less parasitic capacitance, right? So in terms of the speed, telescopic is faster, right? We can make the faster feedback amplifier, but the folded cascode, it can has the larger output and input swing range, right? Although the telescopic is faster, its input and output range is limited, right? So there's the pros and cons. You have to understand and determine which topology you would like to use, right? You need to decide that based on the signal range and as well as the speed, right? To determine the speed, you have to calculate the location of the second pole, right? The non-dominant pole have two. Calculation is important.